Okay, so I'm gonna erase that. I'm gonna put some assumptions. Remember how we did for my transistors, a whole list of assumptions? So I'm gonna do some assumptions on this thing. First of all, we didn't talk about this yet, but part of what op amps do is they have a very, very high input impedance or input resistance. Impedance combines everything. But my op amp has a very high input impedance. So that means input currents are approximately 0. If my input impedance is like 1 mega ohm, and my input voltages realistically are probably going to be down in millivolts or volts, then I'm essentially going to have 0 current in compared to everything else. Remember how we did the same assumption for my transistors for the input current? This is even more true. My electrical engineers will scoff at assuming 0 input current for the transistors because it's actually only like 100 times smaller than the current flowing through. No, in this case, it's going to be like tens or hundreds of thousands of times smaller. So they all go, yep, input 0. Same thing, if input's really 0, you don't get anything out. But your inputs will probably be down in the nanoamps, maybe low enough you can't even measure them in lab with our equipment. That makes solving problems pretty easy. Yeah.
So should we expect anything like that to occur in lab?
If you have 0 input current, then you won't see an output. If you see an output, that means you have some current. But your current's going to be dinky. If you can measure down into the microamps, okay. But these currents might be down in the nanoamps. Input voltages. The inverting is going to be approximately equal to the non-inverting. What we just saw in the last example, I guess I should explain a little more for we erased it because I was busy saying, hey, maximum 15 volt, is if I have one tied to 0 and the other is about anything, we're just going to max out the maximum number, positive or negative. So that means for there to be any interesting input, this thing's really designed so the two inputs are about the same, and we're only looking at that minute little difference. So my two inputs have to be different, or I'll get 0 out. You can try this, by the way. If you build an op amp and hook exactly the same thing up to both inputs, you get 0 out. But when we put two things that are very close to each other, we're just going to get the difference between them amplified by like 100,000. So a very tiny little difference to the point we can assume the two inputs are the same.
Is there a unit for the amp gain?
No.
Okay.
Voltage gain has no, because, all right over here. Technically, voltage gain is just the output. If you measured the output voltage over the input voltage,
Okay.
which we'll need in a minute, which means you would take volts and divide by volts.
Right.
Incidentally, we talked about this voltage. This is the gain we usually talk about, and that's what we normally are going to be talking about. But I always note you can have a current gain, and you can have a power gain. They're all just the output over. The voltage is what we usually look at and think about most, because that's what we see on our oscilloscopes. That's the easiest to do in labs, easiest to think about. So what we want to do now is I'm going to take and build an amplifier, and I'll show you how it works. The amplifiers I've been showing so far, we can do differential amplifiers. And like I said, they get used for all kinds of instrumentation purposes. They have a lot of practical applications. But the amplifiers we're going to build in here and use in here are very common also. And one of them I'm going to do is called the inverting amplifier. Now, before we do anything else, it does exactly what it says. The output's going to be inverted and amplified, just like our common emitter on that transistor was. So here's my op amp. I'm going to go into the inverting input. Okay, Be aware, there is no standard for which is the top and the bottom for the two inputs. You have to look at the labels. There's also no standard whether you draw the input into the top or the bottom, so you have to look at where the input comes from. If the input goes into the inverting in, then it's an inverting amplifier. If it goes into the non-inverting in, then it's a non-inverting amplifier. Which is on top or bottom, doesn't matter, they're about 50-50 which way they get drawn. It's usually whatever's easiest to draw for whoever draws it. Okay, now I'm going to take the non-inverting input and I'm going to tie it to ground. I'm going to take the inverting input, I'm going to go through a resistor because remember I need to have a tiny current going in, so I'm going to make sure I control that. And the very last thing I'm going to do is I'm going to create negative feedback. I'm going to call that R sub F for the feedback resistor, R sub I for the input resistor. I'm going to call this the input voltage. I'm going to call this the output voltage. Okay, input voltage is not tied to positive voltage or negative voltage. It's just the input. It's a voltage, it's got to come from somewhere. We do it in lab, we'll use a potentiometer to adjust the voltage up and down. Or later, we'll actually hook an AC voltage to it and see it amplify. Okay, real quick, I'm going to go into the negative. That means my output's going to be inverted, right? If I have a positive number in, I'll get a negative out. If I have a negative in, I'll get a positive out. And then what I'm going to do, because this has so much amplification, it's going to frequently be more than I need, so I would go in and I'd go all the way up to the power supply or all the way down to the power supply. To keep me from doing that, I will take some of the output and feed it back to the input. But because my output is inverted, that means if I come in positive, I get negative out and I add negative to the input. So I drive the gain down. If I have negative coming in, I get positive out, which comes in to add to that negative. Drive the gain down, so I constrain my gain. This has two big advantages. Number one, I'm no longer using well, they all come out the same thing. I'm no longer strictly depending on this amplifier's internal amplification. In fact, as long as we're talking purely theory, I don't even need to know what it is. It's going to get the same numbers regardless. In reality, the actual amplifier there will matter, but it doesn't actually matter because it really doesn't matter if this amplifier has a gain of 100,000 or 150,000, because if it has a gain of 150,000, I would get more amplification, but then I would also send more back to the input, so I just drive that back down so it has the same gain. That also has an advantage in that op amps are fairly inexpensive, so if I buy a whole bunch of them and I get two of them that have the same number I'm going to put in there, but they have individual, in reality, maybe not quite as exaggerated as we have, but in reality, one might be 100,000. The other at 115,000, I can plug them both in the same circuit and they'll work the same. Okay, let's use my two examples. I'll use my grid blue marker now, just keep it separate. And let's talk through what the gain would be. This is an amplifier. So I'm going to use those examples. So first thing I will do is I'll come in and I will label everything. Notice I don't even have to put my power supply, I'm not even bothering with it. Okay. It will be limiting in real world. But for my calculations here, I can just find out my gain. First of all, what's my voltage? Voltage, ground. What's the voltage? Ground. Yeah. I mean, that's what the definition of ground. It's your 0 point. Okay, so what's my voltage right here? Yeah, 0. My two inputs are the same. Since one of them's ground, the other one is ground. Okay, what's my current into here? 0. Why? Not because that's 0, because we said over there it's going to be 0. What's my current right here? 0. My current into my amplifier is 0. And my two voltages are identical. Now they happen to be 0 in this case because one's tied directly to ground. But the reason they're both 0 is because the one's ground. Okay. Now that I have those down, what's my current going to be right here? I'll call this I sub I for the input current. So by Ohm's law, that's going to be the voltage drop across the resistor. So I'm going to start from Vn. I'm going to end up at, well, 0, all divided by Ri. So I would just take the input voltage and divide it by the input resistor. That's my input current. Now you might ask, well, what's this current? Right here I have a junction. Current flows in. Nothing flows there, so this current better be exactly the same as this. I'll calculate it. So I'm going to call this the current through the feedback resistor. Current through the feedback resistor. I start at 0 volts, I end up at V out. So 0 minus V out, the direction I drew it, over RF. But what I just said, right, this current has to be the same as that current. Because the current in here has nowhere to go other than around. Yeah,
Sorry, RF is the
feedback
copper.
resistor.
Feedback.
The resistor that connects output to input is feedback. Yes, I do realize that our normal concept is more like, here, constructive feedback or positive feedback versus negative feedback. In electronics, we want the opposite. Negative feedback takes things back to the input and pulls it down. Positive feedback means as my output gets bigger, I would feed it back to my input, which would make my input bigger, which would make my output bigger, which would make my input bigger. So this is going, right? An example of positive feedback would be feedback you hear on the stage where the stage monitors pick up the microphones and go out of control and kill your 2.8 kilohertz here. So we don't like positive feedback most of the time. That means things are going out of control. Negative feedback controls things. Okay, so my two currents are the same, right? Because I come into this junction, there's no choice. So that means I can set Vn, you know what? I usually put an N on this. I don't know why, but I'm pretty sure that's the way it is on the sheet. So I'm going to write it that way. Sorry. Okay, so Vn over Rn equals minus V out over RF. Then I can come in, I need V out over Vn as the gain. So I'm going to divide both sides by Vn. And I'm going to multiply both sides by RF. In fact, I'll do the negative RF. So Vn cancels here. RF cancels there as well as the negative. So I'm left with V out over Vn. So my gain, my voltage gain is V out over Vn equals minus RF over Rn. So when I build one of these, I can just take the feedback resistor and divide by the input resistor, and that'll tell me the gain. Guess what? You're going to do these in lab, and these are pretty much spot on. Like, this is not a rounding difference. If RF is 10 times bigger than Rn, then your output's going to be 10 times bigger. Has a negative because it's going to be inverted. If your input's positive, your output's negative. If your input's negative, your output's positive. What's the output voltage for my example there? Well, gain is minus RF over Rn. which is minus the feedback resistor is 12 kiloohms. The input's 1 kiloohm. So my gain of that amplifier is minus 12. Output over input equals the gain, therefore the output equals the gain times the input. V out equals gain times the input, which is minus 12 times 100 millivolts, which is minus 1.2 volts, right? 100 millivolts is 0.1 volts. So your output's 12 times bigger. Oh, there is a decimal. It's kind of bad on the walk away. There you go. Decimal. It's 12 times bigger, and it's negative when the input's positive. If the input were minus 100 millivolts, you get 1.2 volts out. If my input here, instead of just being a DC voltage, was an AC voltage, my output would be 180 degrees out of phase and 12 times bigger. Only won't be as if we, if the voltage ends up going past the rail, what we call the rail voltage, the supply voltage. How about if I want to go find currents and such on this? What would the current be right here? Current is going to be 100 millivolts minus 0, because that would be 0 volts, right? Over 1 kilo. 0.1 milliamp. Sound right? 0.1 over 1,000? Yeah.
So where'd you get the 100 millivolts, or you just make that up?
That was my input on my initial problem.
Oh, right.
That also means this current around here would be, oops, that's right, the input voltage, 0.1 milliamps. 0.1 times 12 is 1.2 volts. So I end up with my 1.2 volts at the negative, because I'm going from 0 here, well, I'm going to my direction of minus 1.2 volts. But I think these are a lot easier to work than our transistor circuits were after we get to this point. The complication building them, honestly, for most people is you have to have positive power, negative power, and ground. Shouldn't be that bad, but just make sure you don't short any of them. For some reason, every semester somebody tries to short positive and ground, or negative and ground. Don't do that. This is like short positive and ground. Okay. That's my inverting amplifier. Now what I'm going to do is my non-inverting amplifier. So I'm going to erase this stuff I have right here. And I'm going to change this. Non-inverting amplifier. On top, I'll put the non-inverting input. I'll go straight into it. I will take the inverting and I'll run it to ground through a resistor. I'll call this R sub G for the ground resistor. Here's my output. And the feedback resistor. I still have to take my output. I don't want to take it to my input. I got to take it to the inverting input. That way it's negative feedback. If I took it to my non-inverting input, it would be positive feedback. Incidentally, just out of curiosity, can you think of a circuit where I could use positive feedback? It's fine if you don't. But an oscillator circuit. So I don't have an input, I just take the output and send it back to the, well, I do have an input, but it's the output. I just send it as positive. And then if I use an inverting amplifier and do positive feedback for an inverting amplifier, then it keeps keeps going back and forth to the rail voltage. So I just have a DC power that produces a clock out. Or if I use my RC circuit that we learned from the week on capacitors, then I can make it take time to go up and down, and I can actually produce a sine wave out. So that's how I build it. If you know what LFO is, low frequency oscillator, we can build with that. Next semester, just something to look forward to. So yes, I can't. Just to answer, yeah, there are places I use positive feedback. We won't be doing it here, but we can. All right, my inverting amplifier. Let's see how it works. So my voltage here is Vn, so my voltage here is Vn. That's why I have to have a resistor to ground, because I have to be able to drop that voltage, because these both have to be Vn. This current is 0. That current is 0. So I have a current right here. This current is going to be the voltage, Vn minus 0, because ground's on the other side, divided by the ground resistor. I'll have a current that's going to go from the output, ground. That will be V out, not minus 0, because over here is a voltage that's not 0, it's the input voltage. So it's actually V out minus Vn over the feedback resistor. Now if I look at this spot right here, this current flows in, this current flows out. There's 0 that goes up there. So these two currents have to be identical. Like maybe I should have put this as G and F. So there's just one current that's G and F, and that is this Vn over Rg equals V out minus Vn over Rf. I need to get V out over Vn, so I'll do the same thing as before. I'll divide both sides by Vn. I'll multiply both sides by Rf to get it out of this side. Vn cancels with Vn, Rf with Rf. So I'm done. I'm going to end with Rf over Rg equals V out over Vn minus Vn over Vn, which is 1. I got too fast on that, right? So I'm going to divide by this, and it's V out over Vn, Vn over Vn, which is 1. So my gain is output over input, which is equal to the feedback over the ground resistor. Add 1 to both sides to get that over there, plus 1. So I'm all done with this one. Last one, the gain was the feedback resistor over the input resistor with the negative sign because it's an inverting amplifier. The output has gain, but it's been flipped over. 180 degrees out of phase for like a sine wave, or if it's a DC voltage, the output would have been the opposite polarity of the input. This is a non-inverting amplifier. Therefore, my output is exactly the same polarity as my input, just bigger. But in this case, it's the feedback over the ground resistor plus 1. So let's go build this as an example. I'll take exactly the same things I did last time. 100 millivolts. One kilo ohm, 12 kilo ohms. This is my output. What's my output voltage going to be? Well, my gain is feedback over the ground plus 1, 12 kilo ohms over 1 kilo ohm plus 1. 12 plus 1 is 13. So V out is equal to the gain times Vn, which is 13 times 100 millivolts, or 1.3 volts. So my gain's actually a little bigger for the same resistors for the non-inverting circuit. Not much, just a little bit. If my input was an AC signal, it would look like that. My output would be 13 times bigger and exactly in phase. If I wanted to come here and calculate this, my current right here would be 0.1 milliamps. My current right here would be 0.1 milliamp, just like I got before, right? This is 100 millivolts. So I would have, to get that current, I would have 100 millivolts over 1 kilo ohm. Over here, this would be, my output is 1.3 volts minus 100 millivolts, just 0.1, over 12 kilo ohms. Do not forget on the feedback resistor. This is very tempting to take this voltage minus 0, but it's not. It's the voltage across this resistor. So it's that voltage minus this voltage over that resistor. And you should get exactly the same current for both. That's what we're going to do in lab this week. You're going to build a non-inverting amplifier. You're going to build an inverting amplifier. There will be an amplifier circuit for sure on the next week's exam and on the final. So their calculations, though, mostly come down to, I've got these two gain calculations we've already proved right here in class, so you just use them. And then your ideal, input currents to the amplifier are 0 and the two input voltages are identical. In your lab, you're just going to build one of each of these. And you're going to do them with DC voltages and change the voltage input using a potentiometer, just like we did with the transistors a couple weeks ago. And then you'll hook up an AC signal and watch it get bigger. Questions? You're very quiet. You're a quiet group as a whole, so I don't know if it's that you're just quiet, you understand it all the first time, you're baffled to the point you don't understand it and don't want to ask, or I'm too intimidated. I'm not sure which it is. Hopefully not intimidated. I got a question for you. This is a very common circuit design. Any idea what that does? What kind of amplifier is it?
Non-inverting.
It's non-inverting. I go in here. What would the gain be? What's my feedback resistor? 0. It's a straight wire. What's my ground resistor? Doesn't exist. You can make it really big. If you don't like the infinity symbol, you can make it just big. So I take 0 and I divide by infinity plus 1. 0 divided by anything is 0. Any real number divided by infinity is also 0. So we're good. You can't do 0 divided by 0. That doesn't work. It's not defined. You can't do infinity divided by infinity. That doesn't work. You also can't do infinity divided by 0. That doesn't work. But 0 over infinity, we're good. It's 0. So what does that have a gain of? 1. My output is exactly equal to my input and perfectly in phase. So what have I just made? An op-amp buffer. My output voltage is identical to my input voltage. However, my op-amp has a power supply we didn't draw on there, which means it has the ability to boost current. Remember, my input needs very, very, very little current, probably down the nanoamps. However, my output can push out lots of milliamps. So if I would like to have a stage that pulls off something that provides very little current and then provide a lot of current to drive the next stage, boop, op-amp. No resistors necessary. Do need a power supply. And then I tie the output directly to the input with a wire. Again, buffers, very boring, but where you need them, you need them. You don't drive current, you need them. Input stage of most things will have a buffer in it, ready to go. if you need to drive passive, something after a passive device. And I think it's fun, well, it's fun, it's illustrative, I guess, because you can look and go, I can solve this, but obviously most people look the first time and go, what are those values? Well, you have a straight wire, so it's zero resistance. You have a non-existent resistor, so that's infinite resistance. So you can solve for it. Okay, standard packages for these. The op amp you're going to work with this week is called a 741 op amp. And I'm going to draw it up. 741 op amp. They've been around forever. They're 50 years old. They're probably the second most common transistor ever, or transistor IC ever made. After that 555 one I mentioned next week. They have 4 input pins. Pin 1, 2, 3, 4, 5, 6, 7, and 8. So 1. The way these work is they have an input. Oops, I wrote these in the wrong order. By the way, this is on your sheet. So your 2 inputs come into here, and your output goes to 6. 7 is your positive voltage, 4 is your negative voltage. And I'm going to screw this one up. I should know the 2 inputs, but by the way, if you ever need to look one up, I'm pretty sure if I just type 741 and nothing else, the first thing I get is an image of it. All right, so it's the inverting input here, non-inverting. This is the output. These are called offset nulls. Leave them disconnected. I've never used them in my life. They have uses. I'll tell you what they are. This one is actually just not connected internally. This is a standard package. You have even numbers of pins. They ain't 7. Offset nulls are there because when this input voltage comes in, it may not be centered on 0. The offset nulls would allow me to set an offset and adjust it up and down. That's what they're there for. There's other ways to do it, but we won't use them. So my 5 connections I'll need will be positive voltage, negative voltage. The ground's not part of the power here, but the ground will be part of the circuit because both circuits go to ground. Not negative voltage, ground. Your input will go to the other one, and your output will be just off pin 6. You're going to have a feedback resistor that goes from the negative input to the output. Don't feel ashamed to use 3-dimensional space and just plug it in on top of the transistor. So if I want to build this thing, if I want to build my inverting amplifier, I'm going to come over, I'm just going to put a resistor right here and the feedback resistor go from output to input. I'm going to put another resistor over here and go off, not the power supply, but I'll plug my input into that. Two resistors. This won't work yet. You're going to connect that one to ground with a wire. Okay. I have videos out there I've already put out on how to build this. So I'll show you. I'll go back and do a demonstration. I know it's about time for those of you who got to run to the class. But I do have those out there. I do want to emphasize, when you watch the videos, please make sure you are learning what I'm doing and not just trying to by rote follow me. That also will mean things like use the good benchtop equipment here. I use the little handheld one because it sits right on the board while I'm building. But I would never use that in here. I just use it because we have one camera and one space, and I'm not up to putting multiple screens together for you. So, have fun building. I think we're good. I think we covered everything that I need to for the week. Thursday, I'll cover anything you want to on op amps if we see a gap or something. Otherwise, if anybody wants me to show you how to build, I'll go back and do that now. Or if everybody's working in older labs, I'll let you work.